If I were to show you this image and ask you what it is, you'd probably immediately tell me that this is a dog. The question then becomes, how do we do this as humans? Well, first we look at low-level patterns such as edges, texture, and color. Then we expand to mid-level patterns such as shapes. For example, here for a dog, we have a pointed ear and round eyes. Then we go to more high-level patterns like object parts, where we look at a head and a body for the dog. And then finally, we have our final detection or prediction of what we see. So for example, the whole object here is a dog. The question then becomes, how do we get AI to do this? Well, the first thing we may think of is a standard feed-forward neural network. So our input here, again, is going to be the picture of the dog, where we have an 800 by 600 by 3 photo, where 800 here is the height, 600 is the depth, and 3 is the standard RGB color information that we have, since this is a colored photo. So we can convert our image to a matrix, and we get this matrix representation, where again we have the same size, 800 by 600 by 3, and the values here represent individual pixels within our image. And then what we would do is flatten this matrix, so basically take every one of the rows and add them together end by end. So we would get 800 times 600 times 3, which is 1.44 million, and then we can feed this flattened matrix representation into a feed-forward neural network, where in our first layer we have 1,000 neurons, then 300, then 64, then 64, and then 1, and the final value tells us the probability that this image is a dog. And we have three main problems with doing it like this. One is the computational explosion that we see here. Two is the loss of spatial structure as we flatten our matrix. And three is that we have no translation invariance when we input our matrix directly into our feed-forward neural network. So if we first take a look at one, computational explosion, we can again zoom in into that portion of our figure where we have 1.44 million data points going into our feed-forward neural network. And this is a very nice image here, but in reality, what we get is connections between every single one of these, and every single one of these red lines is a parameter within our network that we need to think about. So the number of parameters that we need to learn becomes 1.44 million times 1,000, which becomes 1.44 billion. So first, this is a memory explosion in that we have to track and store each one of these parameters within our network, and this is only for one layer. Secondly, we have a massive computational cost in that when we do back propagation, we have to fine-tune each one of these parameters over and over again. And third, again, because this is 1.44 billion parameters, we have the risk of high overfitting. So the second thing we need to think about is loss of spatial structure. So if you think about going from a matrix representation and flattening this out, we get a removal of spatial representations and relationships. First, we're removing neighborhood relationships, and that values here that are together are not going to be together in our flattened version. Second, we have a loss of spatial patterns, so edges and shapes that here are together and relative to one another, whether they're higher or lower to one another, get flattened out in our final vector that we get. And finally, by flattening, we prevent learning of spatial correlations. So within this matrix that we have here, so if in one area we have something that represents one thing, and in an adjacent area we have something that's relevant, once we flatten this out, we don't preserve this information together. So we can think about this within our example again, where we have the dog, we have our matrix, and let's say for a simplicity case that this green area represents its head and this red area represents its body. So if again we space this out and we say that we want to first take each row, separate it, we can see where the head and the body representations line up. But then when we flatten our matrix that we have, so we can see that one part of the head is separated from the other part of the head, so the spatial representation doesn't line up, and we would get the same thing for the body as well. So although in our matrix that we have a very nice visual of where things lie, once we flatten this, we lose all sort of spatial representation. And finally, we deal with no translation invariance. Simply put here, the image of the dog is converted to this matrix here. Our neural network is not learning specific features of the dog like a human may. So for example, it's not learning this is a dog's eyes, this is a dog's ears, this is fur, etc. It's literally memorizing this matrix and saying when these values are these specific numbers, then this means that this is a dog. So this means that the neural network treats every pixel independently, and there's no generalization across image positions. So the model sees a shifted dog as new and as a non-related pattern. So we can see, for example, if we rotate the dog in 360 degrees, or if we flip it horizontally, we see that it doesn't recognize this as being the same dog, since it's not learning features, it's just memorizing the position of the dog in this specific photo. So we can see from those 3 points that learning from a feed-forward neural network is not very good. So what we want to do is something that's more similar to human intuition. So where we have low-level patterns, mid-level patterns, high-level patterns, and a final detection. And this is where convolutional neural networks come in. So in a convolutional neural network, we use a convolution filter to automatically learn spatial patterns and data. So a convolution filter is also known as a kernel, and it is a small matrix of learnable weights that slide across an image performing dot products. This operation produces a feature output map that highlights the learned patterns, so this includes again edges, textures, fur, let's say for a dog, etc. So we can look at an example here where again we have an input image of a dog sitting in grass, and we have specific kernels, so again matrices that we would slide over this image. And each one of these kernels detects different things. So this red one here, for example, detects the edges, this one detects the texture, and then the blue one detects the brown areas within it. And we see here that we get our output feature map. So once we slide this kernel over our input image, we get something that looks like this out here, where it basically highlights all of the edges that we see. In the second case, this detects the texture, so our output map will show all of the texture. And in the third case, our third kernel detects all the brown areas, so we see all the brown areas. So you can think of this in a very simplistic case as, let's say again, we have 3 kernels here, that the first kernel may be able to detect the ears, the second one the eyes, and the third one the nose relative to our input image over here. However, convolutional neural networks aren't this explicit, so each kernel captures certain visual patterns. However, in reality, CNNs don't have distinct filters that isolate semantic parts, so they don't actually capture eyes and ears. So instead, many kernels work together to represent low, mid, and high features that collectively capture what makes an image dog-like. So early filters, for example, may highlight edges and gradients. Middle filters may respond to textures and shapes, and late filters may capture abstract configurations relating to the object identity. So if we use a CNN, how does this relate to the 3 problems that we had with respect to computational explosion, loss of spatial structure, and no translation invariance? Well, first, for computational explosion, before we had in our traditional feed-forward neural network, the problem that we had a lot of parameters that we would have to learn. So again, when we had 1.44 million as our flattened vector, the number of parameters that we had to learn became 1.44 million times 1,000, which was 1.44 billion, and we had problems with a memory explosion, computational cost, and overfitting. Unlike this, a CNN has filters, and these filters are the weights that we actually fine-tune and learn. So instead of having 1.44 billion parameters to learn, here we only have 9 relative to this specific kernel. So this means that we don't learn weights per pixel of our input image. Instead, we learn a small kernel that's reused across this image that we slide over one by one. And the kernel focuses on a small portion of an image at a time. So in this case, we don't need to connect every pixel to every neuron. The second problem we had was a loss of spatial structure. So this happened when we flattened our input matrix. So here we had the removal of neighborhood relationships, a loss of spatial patterns, and this prevented us from learning spatial correlations. So in the case of a CNN, we have a retention of spatial relationships because we slide a kernel 1 by 1 or 2 by 2 or however many we decide over the image, and we use the same kernel over and over again. So kernels slide across the image in 2 dimensions, neighboring pixels stay neighbors, and the network preserves spatial structure as we see here. So in the third case, when we had no translation invariance, this meant that if we gave the neural network an inputted image of a dog that was flipped horizontally or flipped vertically or zoomed in or zoomed out, it wouldn't recognize the image as being the same dog or a dog at all. So the neural network treated every pixel independently, there was no generalization, and the model sees a shifted dog as an unrelated pattern. However, in a CNN, again, we have filters that are applied throughout the input matrices, so the features identified are regardless of location. So the same kernel is reused across the entire image, which means that features are learned at the top left, also identified elsewhere. And the fact that we use the same kernels over and over again means that the network doesn't have to care about the location of where something is. So if the dog's eyes are in this location rather than up here, it'll recognize it just the same. Now that we've recognized that CNNs are a great tool to use for image classification, in the remainder of the video we will cover the 4 key components and parameters of a CNN. So this includes convolutional layers, which are kernels as we discussed, pooling layers, stride, and padding. We'll talk about the overarching CNN architecture, and then go over a coding example and representation. To begin, a kernel, also known as a filter, is a small matrix of numbers. It slides over the input image, which is a matrix, and performs convolutional operations. So this convolution operation is just an element-wise multiplication which sums to a single value. So here in this numerical example, we have the pink as being the input and the white as being the filter. So we multiply, for example, 0.7 by 0.3, 0.2 by 0.1, 0.3 by 0.2, and then we sum up the values to get one individual value. So a kernel doesn't necessarily need to be a square, so it can be 2 by 2 or 3 by 3. but it also can be non-square. Non-square kernels are used when data has different dimensions of importance. So for example, text in images is horizontal, not vertical, so you may want something like this. Each kernel looks for specific patterns in the input. So again, this can include edges, textures, shapes, etc. And the output of applying a filter is a feature map which highlights which feature appears. The values inside the kernel matrix are weights unlearned during training. So if we look at a numerical example here, we have an input matrix which is 3 by 3 by 1 and a kernel which is 2 by 2, and we have a feature map which ends up being a 2 by 2 matrix. So again, we slide this kernel one by one over this image. So in this case, over the first 4 boxes, then the second 4 boxes, then we move it down to these 4, and then finally the last 4. And for each one of these, once we slide the kernel over that area, we do an element-wise multiplication and then sum up those values. So for example, here, if we slide it over the first one, 1 and 1 are multiplied together, then 2 times 2, which we get here, then 1 times 0, which we get here, and then finally 0 times 3, which we get here, and we sum up each one of the values to get 5. And then we do the same thing once we slide it over the second area, this third area, and finally this fourth area. And in the end, we get 4 values. So in this first box here, we get the value of 5, and the second box we get 7, the third box we get 8, and then finally the fourth box here for our output, we get 6. And we can see that our output feature map becomes this exact matrix. So the formula to actually calculate what the size of this feature map is going to be based on the kernel and our input matrix size goes as follows here, where for our input height, we have the input height minus the kernel height plus 2, and then this 2 is multiplied by a padding value, which we'll go over next. And for this, we take the floor value, which means that if we get a decimal, we go down to the closest integer, and then we add 1 to the value. And we do the same thing for the width, where we have the input width minus the kernel width plus 2 multiplied by padding divided by stride. And for our output depth, this just becomes the number of kernels that we have. So here we only have 1 kernel, so this becomes just 1 depth. And if we apply this to our example, the input height that we have is 3, the input width that we have is 3, the kernel height is 2, the kernel width that we have is 2, and then the padding and stride, which again we'll talk about, is 0 and 1 respectively. So then the output height that we get is 2, the output width that we get is 2, and then the depth becomes 1. And our final value becomes a 2 by 2 by 1 matrix, which is what we get over here at the top. The second component we'll talk about is stride, and a stride is a hyperparameter which decides how many steps the kernel moves each time that it slides over our matrix. So for instance, a stride equal to 1 moves across the matrix at 1 pixel at a time, a stride equals to 2 moves across the matrix at 2 pixels at a time, etc. The trade-off of a bigger versus smaller stride is that for bigger strides, we move faster and we have smaller outputs, but then we have less detail that's captured. For bigger strides, we get slower, larger outputs, but more detail is captured every time we slide over them. So for example, a stride of 1, we have first the first 9 boxes, then we slide it over once to the right, then another time to the right, then another time, and then finally we get to the end, and then we slide it down 1 and we start all the way back on the left again. In comparison, if we have a stride of 2, we move 2 to the right every time, and as we're moving down, we also move down by 2 pixels. The third element we have is padding. So padding here helps maintain output feature map sizes and captures edges. So without padding, the output always gets smaller, and with padding, you can ensure that the output shrinks less or stays the same size. Example here is that we have a 3 by 3 input matrix with no padding, and we can add a padding of 1, so this means just adding 1 layer of zeros all around the matrix. And finally, we have pooling layers. So a pooling layer compresses the output feature map. It takes a small window matrix and slides it across the input, similar to a kernel, but rather than learning weights like a kernel, it summarizes the values inside the window. So the purpose of pooling includes making the network smaller and faster. It keeps the most important information while discarding the details, and it controls for overfitting, where it helps to generalize such that small changes do not make a big impact to our learning. Two common pooling methods are max pooling, which takes the max value of each box as the output, and average pooling, which takes the average value of each box as the output. In this example here, we can assume that, say, our stride is equal to 1, and we have a pooling size of 2 by 2, and we can see that our input matrix is a 3 by 3 by 1 matrix here. Again, we slide this over the input matrix in the same way that we would do a kernel. Since our stride is 1, we move it 1 at a time. So here, and then we move it to the right by 1, then we move down and to the left, and then we finally move to the right by 1 again. And again, there's two types of pooling. So in the first case, we have max pooling, which means we take the max value of whatever is in this box. So here in this first box, the max value is 5. In the second box, the max value here is 4. In the third box, the max value once again is 5. And then the fourth box, the max value is here 6. So then our output becomes 5, 4, 5, 6. And if we were to do average pooling, then we would take the average of these values. So we would use the same boxes again. Instead of taking the max value, however, we would take the average. So if we sum these values up and divide them by 4 in this case, we would get 2.75, 2.5, 3.25, and 3.25. And this would be our matrix size. And the formula for deriving the output dimensions is slightly different than the kernels, where here we have the output height is equal to the input height minus the pooling height divided by the stride. And then again, we take the floor plus 1. The output width is the same, but with the width. And then finally, our output depth is just whatever the input depth was. So in our example, if we have a stride value of 1, if we have an input height of 3, and an input width of 3, our input depth is 1, our pooling height is 2, and our pooling width is 2. So if we use all these values and use this formula on the left, we get a 2 by 2 by 1 matrix, which is what we get in the output over here. So if we consider the overarching CNN architecture, let's say in this example that we have an input image that's 28 by 28 by 1, so it's a black and white image that's 28 by 28. As we feed it through the CNN, we want to see how the size of our input data changes as it goes through each layer. So in the first layer, we have a convolution layer where we have a bunch of kernels. So we have 32 kernels that are of size 3 by 3. We have a stride of 1 and a padding of 0. Then from this, we feed it through a pooling layer where we have a size 2 by 2 and a stride value of 2. Then through a second convolutional layer where we have 64 kernels of size 3 by 3, a stride value of 1, and a padding of 2. And finally, we take this output and we flatten it, and then we feed it through our feed-forward neural network at the end to get our prediction. So we need to recall again the convolutional dimension formulas and the pooling dimension formulas. And here we have 4 portions that our data goes through. In the first case, we feed our input image, which is 28 by 28 by 1, into this convolutional layer, and the output of this, given our values, becomes 26 by 26 by 32, and then we feed this 26 by 26 by 32 input into our pooling layer, and the output that we get is 13 by 13 by 32 once we apply these second formulas that we showed down here. And then when we feed in this 13 by 13 by 32 into our convolutional second layer, we get an output of 15 by 15 by 64, once again using our first formulas. And then when we want to flatten this output, we just multiply this together, so 15 times 15 times 64 to get 14,400. And after this, we feed this through our neural network, so we get 14,400 by 1 that's fed in and flattened through this neural network, and we get our output at the end. So one thing to notice compared to our initial feed-forward neural network is that here we're not flattening the raw image of the pixels like we do before. Instead, we're flattening the representation that we get at the end. And that's because convolutional and pooling layers extract useful global and local features before flattening, then afterwards produces a smaller feature vector with richer information that we can learn from rather than feeding this input image with all of its pixels directly into this flattened portion. So if you look at a coding example here where we use PyTorch, we have a custom CNN that's of the similar size as we looked at just now. So in the first case, for example, we have an input size of 28 by 28 by 1, and our operation is a convolution. So here, for example, we're defining that we have a convolution layer. We're saying that the number of input channels or the depth is 1 as we have here. The output channels or the output depth is 32, which we get as the output here. Our kernel size is a 3 by 3. Our stride is a value of 1. And our padding is a value of 0. Then our output from this layer, which is 26 by 26 by 32, is fed through our second layer, which is a max pool, which has a kernel size of 2 and a stride size of 2. If we use the formulas from the last page, we get an output of 13 by 13 by 32. The third layer, again, has a convolution with an input channel size or depth of 32, which we can see from our last output, an output channel size or depth of 64, and then a kernel size of 3 by 3, a stride of 1, and a padding of 2. We then flatten this output, so 15 by 15 by 64, which multiplies to 14,400, and then we feed this through one dense layer, which has an output size of 128. And then a second dense layer, which has an output size of 3 by 1. And you can think of this 3 by 1 output size as being 3 values, which add up to 1, since we have here a soft max output, which gives us probabilities for whether this is a dog, a cat, or a rabbit. So here, for example, we get an output that there's a 71% chance that this is a dog, a 23% chance that this is a cat, and a 6% chance that our image is a rabbit. So to summarize this video, we went through the intuition behind image classification. We went through the shortfalls of using traditional feed-forward neural networks for this task. We went through an introduction of convolutional neural networks and their strengths. We went through the key 4 components and the parameters of a CNN, which are convolutional layers or kernels, pooling layers, and then also stride and padding. We went through the overarching CNN architecture, and then went through a coding example and representation. Thank you for watching this video. Please consider subscribing on YouTube and following us on Instagram, and also supporting us on our Patreon.